Hello everyone! Welcome to the next video of the series Calculus in Nutshell. In this video, we're going to explain one of the fundamental tools of the calculus, known as derivative. Derivatives are used to model rates of change in many real-world applications, such as estimating the behavior of moving objects, predicting the market trends, or to find the optimal points of economic functions to maximize revenue. In seismology, derivatives are used to find the range of magnitudes of earthquakes. Derivatives are also used by meteorologists to estimate the weather. And in almost every field where rate of change of the functions can provide some useful results. Now, from our previous video, we want to estimate the slope of tangent line for any point on curve a of x equals x squared. Suppose we increase the side length of square by delta x, then from the figure, the area of the extended portion or value of delta a will be equal to 2 times x delta x plus delta x squared. Now, if we reduce the value of delta x, then what happened to the area of the orange-colored square at the corner? We can examine this more precisely by looking at how the numerical values are related. For increasingly small value of delta x squared becomes so tiny that it begins to vanish. By looking into the area of orange color square at the top portion, we can observe that delta x squared gets smaller so much faster than delta x that we can remove it from our calculation entirely, leaving change in area delta a equals 2 times x delta x. When we are throwing delta x squared and makes delta x infinitely small, we're moving from a finite numerical approximation to a direct statement of the instantaneous rate of change. To indicate this, we change notation. So the result we were looking for, that is, the slope of the curve, is given by the equation del a over del x equals 2x. The important point for us to remember is that delta x represents a finite change in the value of x, while dx represents an infinitely small change in the value of x. Mathematicians have built more sophisticated tools around this idea to make sure things don't go wrong in complicated cases. But for the functions we'll use in this course, it will work perfectly. For more clarity, let's solve one more problem. Consider a cube of side length x. If we increase each side by delta x, then the added volume represented by the green, yellow, and red blocks will be 3x squared delta x plus 3x delta x squared plus delta x cubed. Now, as delta x shrink, the volume of the red and yellow blocks shrinks close to 0. Just like with the square, delta x squared and delta x cubed shrink faster than delta x, leaving change in volume delta v equals 3x squared delta x. We can consider the infinitesimal changes dv and dx and get rate of change of volume dv over dx equals 3x squared. In each of the last two cases, we were able to find the derivative by substituting x plus delta x in for x, and eventually using infinitesimals to solve for the instantaneous rate of change. Using the substitution trick above, we can tackle a real-world problem, and one of the main uses of derivatives is finding the lowest or highest value of a function. But that we'll discuss in the next video. Until then,